Greetings everyone, this is Puya. Today's topic is about stacks. If you remember last time we talked about abstract data types. Now there are different abstract data types. One of the main ones is stack, which is a linear abstract data type. In this lecture, we'll focus on the concept of stacks, and we also see how to implement it using arrays and linked lists in C++. We also see some applications of stacks. So stack is a data type in which items are inserted and removed from one end. So if you remember from the lecture on abstract data types, each abstract data type is a collection of data and also the operations associated with those data. So a stack is a container of data. You can think of it as a container of data that you only have access to it from one end. So you insert data and remove data from only one end, which we call top of the stack. An example of that is the plate holder in a restaurant or a kitchen, in which you only place the plate on top of the stack of the plates that you have, and also remove from the top. So we can only take from or insert on the top plate, which is going to be the last one. An abbreviation that's used to describe stack is last in, first out. It means that the last item that you place is the first item that you remove. Or also you can think of it as first in, last out. The first item that was placed in the stack is the last one that gets out, that can be removed from the stack. Some applications of it, which you have already used many times, is, for example, the backward button or forward button in web browsers. So this is how you can access to the last website that you checked out, right? So this is like, you can think of it as a stack of websites that you can just like access the last one that you checked out. Or similarly, the undo or redo button in like many software packages like Word or Excel or text editors, like these keeps all previous changes in a stack. So like these are like items that are placed in a stack. There are many other stack applications in programming and compilers, which we're gonna see in this lecture. Backtracking is used in all of these examples. So like because of this concept of last in, first out, you can access the last item in the stack. This is a process when you need to access the most recent data in a series or in a collection of data that you have in your stack. So this website provides a good animation for application of a stack. Maybe I should show you how this works. So like you can think of this as a stack, and like I'm just gonna push. So like there are two terms that are associated with a stack, and first one is push, which is basically inserting data in your stack, and pop, which is removing the data from top of the stack. Okay, so this shows stack implementation using arrays. So if I push this, it would basically push this in the top of the array. And another one, push, it's just gonna go here. And this is basically the index that we're gonna use to keep track of where the top of the stack is. Okay, so you see that here we have an array of 30 elements, but we're using only, like at this point, like we're only using 2 elements of it. I can just like add another one. So it means that the next item that we push, it's going to be placed at this index of the array. And it can go on. If I pop, can you guess which element is going to be removed? Is it going to be this one, or this one? So you only have access to the top of the stack, right? So like you only can remove it from the top. So if I remove it, it's going to remove it from here. If I remove another one, it's going to remove this one. If I push another one, it's going to place it in the top of the stack, which is going to be this element. Okay. So the property of a stack, as mentioned, is last in, first out. The last item that was inserted, it's going to be the first item that's going to be removed. The main 2 operations associated with the stack, or the main 2 functions associated with the stack, are push and pop. So the insertion of data elements in the stack is called push. So this is like how you push elements on the top of the stack. You can see that like you only have access to the top of the stack. Removing data from the stack is called pop, and removing, it's just gonna be again happening only from the top of the stack. So this is like how you pop the elements from the stack. So just an example here, we have an empty stack. We have an empty stack first. When we push 12, then we have only 1 element in the stack. When we push 13, it's going to be placed at the top of the stack. So we have like 12 and 13 on top. Push 14, we're going to have 12, 13, 14. Push 15. When we pop again, it's going to be only accessible from the stack is only accessible from the top, so it's going to be removed from the top. Another pop, another push, and this is how it's done. So this question is asking, like, if we want to change this stack into this stack, what do we need to do? Right, you see here they're almost the same, but the middle element is different, right? We can't access the middle element, right? We only have access to the stack from the top. So what we need to do is basically pop this one, push 14, and then push 16. So this is how this is going to be done. Pop, pop, push, push. One main difference between push and pop is that push, it's a void function. Means it doesn't return anything, right? It just like does a certain operation, which is inserting the data into the stack, the pile of the numbers that we have. However, pop basically removes the item from the stack and returns the value of it. So it has a return data type, which is in this case can be integer, but it can be any kind of data type. So it checks out the last item and put it in a certain variable and return it, and at the same time removes the element from the stack from the top side. So this basically shows an empty stack. We're pushing 1, then pushing 2. If you want to pop, it's gonna remove it from the top. 2 things that we have to make sure that we follow when we want to push or pop. When we want to pop from a stack, we have to make sure that we don't have an empty stack, right? Because if you have an empty stack, like there is no element to be removed from the stack. So whenever we want to pop, like this is a requirement that we have to check. Just like if stack is not empty, we can pop it. And the other requirement, which is related to the push operation, is that we have to make sure that our stack is not full. Like each stack has a capacity, right? So like if you implement it using array, in this case, the size of array is finite, is bounded. So you have to make sure if you want to push a new element, a new data item into the stack, your stack is not already full. So this is a requirement for the push operation. Excuse me. So just like a very basic, simple practice question, what's the output of the following pseudocode? So here we have an empty stack. Let's assume that the stack is empty. We are pushing 3, so we would have 3. We push 2, so 2 goes on top of the 3. We pop from the stack, so it's going to remove from the top, which is the number 2. And you can see that here, pop, it returns something. What is it that it returns? It's the number that got removed from the stack. So it goes and stored as is stored in the item variable. My stack dot push 4. So like we only had number 3 in the stack. Now we pushed 4. So far we have 3 and 4. And again, like we push another data element in the stack, which is the variable item, which we stored number 2 in it. So it's gonna, our stack becomes 3, 4, and 2. And as long as the stack is not empty, we're gonna pop the elements out of it, remove the elements out of it, and store it in the variable item, and we print it, we write it, however it's done in any programming language. So our stack is 3, 4, 2, and you remember that we can only remove or pop the elements from the top. So the first item that's going to get popped, it's going to be 2, then 4, then 3. Okay, so the output of this is going to be 2, 4, 3. Stack abstract data type is a list or collection of finite data with the constraint that insertion, access, and deletion operations can be only performed one at a time and only from one end, which we call top. So therefore, last in, first out, or first in, last out. Okay. One important feature of the stack is that stack is a linear abstract data type, and its time complexity is big O notation 1. It means like constant time for insertion, access, and deletion operations. What this means is if you want to insert or push, or if you want to pop any element out of the stack, it doesn't matter how many elements you have in your stack. If you have n elements out of the stack, like if you have 10 or 100, 200, 1 empty, so if like you want to push an additional data item into your stack, the amount of time that this push operation it should take, it should be a constant time. Shouldn't matter like how many elements you have in your stack. The same thing for your pop operation. Another operation that we have is peek or top, which you can just like see the value on the top of the stack. You don't remove it from the item, you only like check out the value. That's the same concept, like it's a big annotation of 1. It means like constant time for any of the push, peek, and pop operations. We will see how this is important when we want to implement the stack using linked list. So we'll see like how we can implement a stack using linked list, and we have to make sure that the big O notation is 1. It means that like the operation of like the push, pop, or peek operations take a constant time, and no, like doesn't matter like how many elements we have in the stack, it should take a constant time. So one application of a stack, which we'll see in detail later, it's the reverse Polish notation, or also known as postfix notation. So this is a mathematical notation to um, um, conceptualize or find the value of a mathematical arithmetic operation. And in this notation, every operator follows its operands. That's why it's called postfix, right? The operator comes after the operands. So this was invented by Jan Lukasiewicz. I'm sorry if I'm not pronouncing it right, in 1920. So like what we are used to is the infix notation, right? In the infix notation, we have to know the precedence of the operators, and we use brackets. So you know that like brackets have higher precedence than the exponential or power, then multiplication and division, then addition and subtraction. So this is what we are used to, right? But compilers, when they want to store or evaluate operations, they do it a little bit more efficiently. So like they don't use parentheses, and like the postfix notation of the same expression is like this. So you can see that the operands have the same order, but what happens here is that like we have number 5, then 1, then 2, then addition, 4, multiplication, summation, 3, and minus. We'll see how to convert an infix notation to a postfix notation a little bit later, but what I can show you here is that like, okay, so like now we have 5, then 1 and 2, okay. And to evaluate this operation, we can use a stack. We'll see how to do this. So these are the terms that we have. We have different symbols. Some symbols are operands, like 5, 1, 2, 4, and 3. And some symbols are operators, like addition, multiplication, and subtraction. There should be a delimiter. So like in this case, like for example, we use a space to like as a delimiter between the symbols. We can use comma, but the excuse me, the algorithm to evaluate a postfix notation is given here using a pseudocode. So you go through this expression from left to right. What you end up doing is putting all the operators, putting all the operands in a stack. So if the symbol is operand, you store it in a stack. So in this case, we have number 5 first, then number 1, then number 2. The next symbol that we read is an operator. So what happens if the symbol is the operator? What we do 2 pop operation. So as you remember, like our stack has number 5, 1, and 2, right? What we do, basically we pop 2 and 1. What we do, we store the first number or the first item that got removed from the stack on the right side, and the second number that got removed from the stack on the left side of the operator that we just read. And we evaluate the expression. So like right now, we only have number 5 in the stack. We popped 2 and we popped 1. 2 goes on the right side, 1 goes on the left side, and we evaluate 1 plus 2, which is going to be number 3. Okay, and the result, it's going to be pushed back into the stack. So our stack is now number 5, then number 3. Okay, and we keep reading it. The next symbol that we have is number 4. Excuse me. If it's which is an operand, so what we do is like store it in or push it into the stack. So our stack is now 5, 3, and 4. The next item that we have, or the next symbol that we read, is multiplication. So whenever you read an operator, you have to do 2 pop operations. Our stack is 5, 3, and 4. We pop 4, goes on the right side. We pop 3, goes on the left side of the multiplication operator, and we evaluate this operation, which is going to be 3 times 4. It's going to be 12. So the result is 12, and we push 12 back to the stack. So our stack becomes 5 and 12. Okay. The next symbol that we read, or next item that we read, is the addition operator. Okay. Again, whenever you read an operator, you have to do 2 pops. So number 12 gets popped, goes on the right side. Number 5 gets popped, goes on the left side of the addition operator. Now we have 5 plus 12. At this point, our stack is empty. We evaluate the result, which is 5 plus 12. It's going to be 17. And now push it back into our stack, becomes 17, right? Now we only have one element in our stack. The next symbol that we read is number 3. We push it back to the stack, so we have 17 and 3. And finally, the last symbol that we read is subtraction. So we have to pop 3, goes on the right side, pop 17 goes on the left side, and we have 17 minus 3. Evaluate it, it's going to be 14. Push it back into our stack, right? And we read all the symbols in our string, so we are out of this loop, right? So what we end up doing, we only have one element left in the stack, which is going to be the answer or the evaluation of this expression. So finally, we just like remove this from the stack and save it or store it in the result variable. Okay, so our stack becomes empty for the next operation, that for the next expression that we want to evaluate. So this is the answer number 14, and you can double check that if you do the infix operation, you get exactly the same thing. 1 plus 2, 3, multiplied by 4, 12, 5 plus 12, 17, minus 3, 14. So RPN or postfix notation uses a stacks to store operands, and it would evaluate the each operation using like the pop operation. And this postfix notation is maybe like it's not very user friendly for us to use, but for the compiler it has certain advantages. So like as you will see later, like there's no need for brackets, and like all the operations are only like evaluated from left to right. So like that's how we evaluate it. Like, and the precedence of the operators, like we don't need to worry about it. Like when we have the expression, right? So to evaluate it, we don't have to worry about it. We'll see later how to convert the infix notation to the postfix notation, and how to evaluate this using stacks in C++ or in other programming languages. You can read more about prefix, infix, and postfix notation um, in this link. So like we covered the postfix notation. We have a similar concept in which the operators come before the operands. That's called the prefix notation, which is something we're not going to discuss in this lecture. But this is infix, this is postfix, and we also have the prefix notation in which the operators come before the operands. Um, if you want to read more about it, you can check out this link. So describing a data structure is the next like the next page of this presentation. What are the storage properties of data structure that was used? Like we used push and pop. Operators were never inserted between other operands. So like when we did this operation, it was only like operated on the last two elements of the stack. So you only had access to the top. So the last item to be entered was always the first item to be removed. So that's why we have the LIFO. And this data structure is a stack. The functions that we used, sorry, like so another. Oh, sorry. This is another application of the stack. Um, So in a C++ program, we have at least one function, which is the main function. But in practical programs, in practical applications, we have more than one function. So we call a function from another function. We pass some arguments to that function, and the function is supposed to return to the calling function to the place that was called from, and might be a void function. So in that case, it wouldn't return any element or data, but it might also like return something. So this data, these functions are independent, right? So we want to know like how the compiler would know where to return to, like which line of the calling function it has to return to, and how does it know the like what are the values that has to be returned, and like where are these values stored. So each function requires a space in memory for its variables and parameters. The space must be allocated and deallocated in an organized way. So when you call a function, right, you would have a space in a memory allocated for the function automatically by the compiler. When you return from a function, that space in the memory has to be deallocated automatically. I'm talking about the non-dynamic variables or arrays or other non-dynamically allocated data that is going to be removed automatically from the memory like when you return from the function. So we want to know like how this is done in the compiler. Many programming languages use something called call stack to implement function calling. So when you call a function from another function, when a method is called or a function is called, its line number and other data are pushed onto the call stack. So for each function, you would have the parameters of that function and the line at which that function was called from the calling function stored in a space in the memory, and it's going to be pushed on the top of the stack. And when a method terminates, means like when a function returns, that space in the memory that was associated with the function call is going to be removed from the stack. It's going to be popped from the call stack. And execution restarts at the indicated line number in the method currently at the top of the stack. So we'll see like what that means. So here in this example that Dr. John Edgar has provided for us, we have many functions. We have the main function, we have the part1 function, we have the part1 copy function. These are non-member functions. We also have 3 methods associated with this class. So remove node, and remove fix. So you will see that the main function at line 39 calls the part1 function. Part1 function at line 56 calls the part1 copy function. Part1 copy function at line 185 calls the remove function. The remove function at line 206 calls the remove node, and remove node at line 271 calls remove fix, and this might keep going on. And these are basically the call stack. You will see that like in the memory we will have the same order for the call stack. The main is going to be at the bottom, part1 is going to be excuse me, on top of the main, part1 copy on top of part1, and so on. And in addition to the local variables of the function and the parameters of the function, the line at which the function was called is going to be stored in that space that was allocated for the function, so that when you want to return from the function, when the function terminates, the compiler would know where to return to, where to go back to. So this is another application of the stacks that is used in the compilers. Top of the stack is the most recently called function. Bottom of the stack is the least recently called method. So you only have access to the stack from the top. So you can only go back to this place when you return from this one, right? So like this one has to be popped in order to go back here. So in other words, like this function doesn't have any access, like when you are when the compiler is running or executing this function, it doesn't have access to any other memory locations from the previous functions, because like you have a stack, you only have access to the most recent element. Information is stored on the call stack about each function is called the stack frame. So each function would have a stack frame associated with it, also called activation record. These stack frames store the arguments that are passed to the function, so like the parameters that the function needs, the return address of the calling function. So like this function was called from another calling function, right? So like when you want to return when the function terminates, you have to know where to return to. So that address is going to be also stored in the stack frame, and also would have space for the local variables of the function. Stack memory is allocated and deallocated automatically without explicit instruction from a programmer. Well, of course, like if this is like dynamic memory, the programmer has to deallocate them explicitly, and is therefore referred to as automatic storage. When function is called, a space is allocated for it on the call stack, on the top of the call stack. This space is allocated sequentially, like it means that like it's going to be in contiguous memory locations. So first function, then the second function, then the third one, then the fourth one, and so on. Once a function terminates, the memory it used is no longer required. So it's going to be popped or removed from the call stack and becomes available for the next function call. Execution returns to the previous function and would return to the exact line where the function was called from. And the calling function becomes now the top of the stack. So this is like an example of a call stack. Each of these is the stack frame associated with these functions. I only have one instance of, or one snapshot of this call stack, but you can see that here each function would have its own local variable. So for example, the main function would have n, array, and sum. So that's like here. The main function now calls the square array function, which is here. The square array functions stack frame like goes on top of, or activation record goes on top of the main stack frame, and this one would have the parameters, which is a and n, okay, and also has the local variables I and x. Also, like one thing that's not shown here, it would have the address of, or like the line number of the like the calling which happened in the main. So like you can see that the line numbers are also going to be stored there. And the same thing happens with the square array. Square array is going to call the power function. So the power function would have its own memory space or stack frame. It would have all of these local variables and the parameters. And once this power function is terminated, this stack frame is going to be removed from the call stack, and the control would go back to the corresponding line from the square array, which is going to be this line. That's why the line at which the function power was called has to be also stored in the call stack. So this is a good example of the call stack and functions. So that's another application of stacks that the compiler uses. In the example, functions returns values assigned to variables in other functions. They did not affect the amount of memory required by previously called functions. So like when you're here, the memory of the square array or the main is not going to be impacted or affected. This function below them on the call stack did not affect. Stack memory is sequentially allocated. It's not possible to increase memory assigned to a function previously pushed onto the stack. Okay, so like because this is a stack, you can think of a stack as a container, three-sided container. You only have access to it from the top. So when you're here, right? When this is the most recently called function, nothing can happen to main storage or square array storage. You can't increase the amount of memory needed by a square array or main when the power is the most recently called function. Stack is a natural choice to store data for postfix notation, arithmetic, or the call stack. Operands or stack frames are stored at the top and removed from the top. Notice that we have not discussed the implementation. So like if you remember from the video that we had on the abstract data type, when we talk about an abstract data type, which stack is a good example of or a good instance of, um, we don't talk about the implementation. So we will see about the implementation of stack a little bit later in this lecture. You can implement it using arrays or linked lists or decks, and we're going to see the implementation of it a bit later. So so again, as you remember from the lecture that we had on abstract data type, for each abstract data type that we define, we need to have some operations that would operate on the data. For stacks, the main operations that we have to implement are push, pop, and peek. Push would insert an item at the top of the stack. Pop removes and returns the top item. So this is very important. So it has a return data type, removes and returns the top item. And peek would only return the top item. It wouldn't remove it from the stack. Okay, this is also sometimes called top. So it would just return the item at the top of the stack. These operations should be performed efficiently, like either in terms of time or in terms of memory. And the definition of efficiency might be different between different abstract data types. And note that the order of the items in the stack is based only or solely on the order in which they arrive. That's why like we call it last in, first out. Some other stack applications that we'll see, some of them in this lecture later on, would be balancing of symbols that happens in many compilers. So for example, if you open a bracket but you forget to close it, right, the compiler would show you an error and would just like let you know that okay, so you forgot to close a bracket. This is like either like round brackets, which are parentheses, or square bracket, or braces, curly brackets. So how this is done, it's done using stacks. So all the um, brackets that are opened are going to be placed in the stack, and when you find the matching closing bracket, that opening bracket is going to be removed from the stack. So if you have an imbalance uh, or if you have the wrong order of the brackets, this stack would not be empty at the end. They would have like something left in the stack. So that shows that you have an imbalance or a wrong order of brackets. So in that case, the compiler would give you an error message that you missed something. We talked about the infix, prefix, and postfix notation. So like how the mathematical arithmetic expressions are evaluated and like converted from infix to postfix is done using stacks. Redo and undo in many text editors or many other software packages. Forward and backward in web browsers. Cache memory can be a good example of a stack. You have like access to the most recent data that you used very fast because like it's at the top of the stack. Function calls or call stack that we just talked about, and recursion, which is like calling a function within the same function. So like this is going to be using stacks, and this is done implicitly. So we don't implement the stack ourselves, but it's done by the compiler. So we have implicit call stack. And stack is used in many algorithmic problems, such as Tower of Hanoi, tree traversing, stock span, histograms, night tour, having queens on a chessboard, a Sudoku solver, graph sorting, many different problems. Stack is a very good um, abstract data type that we can use to solve those algorithmic problems. Uh, Assume that we plan on using a stack that will store integers and have these methods. So like this is what I mentioned, like the push is a void function, doesn't return anything, but the pop would return the top to you. We can also design other modules or other functions that use these methods. So for example, you can have a function that determines if your stack is empty or not, or if your stack is full or not, or a function that would display all the values that you have in your stack. So these are the functions that we can implement. Um, it's a good practice, and this is like how stack is already implemented in C++ in the standard template library to encapsulate the implementation of a stack in a class. So we will use classes to encapsulate stacks. So we would have a class of a stack. Encapsulate means like we mentioned that in the abstract data type lecture. So like to enclose the implementation in a class. And we will have like the private data for the class. We will have the different operations. So in this case, push and pop, or peek and is empty, is full, like different operations as member functions or public methods in the class. So we'll see like what this means when we get to the implementation of class in C++. In this lecture, I'm going to show you how to implement a stack using abstract data type. So like, sorry, we will see how to, I should correct myself. We will see how to implement the stack abstract data type using arrays and linked list data structures. Sorry about my, like wrongly saying like this sentence. And both implementation must implement all the stack operations. So we want to implement push and pop and peek. And I'm going to ask you to implement more modules or more methods for the stack. And this is like what I mentioned earlier about stack time. Should be like the time that is consumed to do the pushing and popping from a stack, or pushing into a stack or popping from a stack, should be independent of the items that you already have in the stack. So it should be of the big O notation 1. Should take a constant time to push an item into stack or pop an item from stack. Okay, I'm gonna stop this recording here and then continue this a little bit later.